So what we're going to do now is we're going to practice assigning oxidation numbers to elements within compounds. And what I want to say is when we're talking about an oxidation number, we're talking about for a specific element. Each element will have an oxidation number. For example, if we take a look at CO2 here, the carbon will have an oxidation number and the oxygen. The overall substance itself is not what we're assigning the oxidation number to, it's each element. Now, if you have a single element that's alone by itself, whatever its charge is going to be its oxidation number. Now, right here, if you take a look at sodium, notice how the sodium has a positive charge there. And because there's no number there, we assume it's 1, so it's a 1 positive. And so this sodium has an oxidation number of 1 positive. When it comes to ions, the charge of an ion is its oxidation number. Now look at this one here on number 1. Look at this one. There is no charge right here, which means it's neutral, which means it's a charge of 0, which means that it has an oxidation number of 0. So elements, when they're alone by themselves, single elements, will have oxidation numbers that are equal to its charge. Now what I want to point out here is there are 2 chlorines here, and so we do have a situation like this. Each chlorine has an oxidation number of 0. So just something to clarify there. Now let's go ahead and take a look at this next one here. This is an ionic compound, and ionic compounds, it's really easy to assign oxidation numbers because oxidation numbers are the charge that they have. And so potassium makes a 1+ charge, so the oxidation number of potassium is 1+, and fluorine has a 1-, makes a 1- charge, so its oxidation number is 1-. And so really these first 2 rules here are really easy. Elements alone by themselves, the oxidation number is equal to the charge. If it's an ionic compound such as this, the charge that the elements make are going to be the oxidation number. Now let's go ahead and move on to number 4 here. This is an example of something where it's not an element alone by itself and it's not an ionic compound. This here is a covalent compound. And for covalent compounds, you really want to focus on number 3 right here. So you really want to focus on number 3. Essentially, you want to assign an oxidation number to fluorine, hydrogen, or oxygen, whichever element it has. And then what you want to do is work backwards to figure out what the other oxidation must be because of rule number 4. Take a look at rule number 4. Rule number 4 says that the oxidation numbers of all of the elements must add up to the charge of the compound. So it must add up to the charge of the compound. So let's go ahead and take a look here. So according to rule number 3, we assign oxygen to negative. So oxygen is a 2-. Now, we don't know what carbon is. We don't know, so we're going to call it X. But what we do know is that whatever carbon is, when we add it with the oxidation number of oxygen, it will have to add up to whatever is the overall charge of the compound. Now, if you take a look here, there's nothing there, which means the overall charge is 0. That's compared to maybe this one where the overall charge is 2-. So because this is an overall charge of 0, it must add up to 0. Except there's one thing that we're forgetting here. This isn't enough. If you take a look here, there's not 1 oxygen, there's 2 oxygens. And so it's not just a 2-, it's a 2- times 2 because we have 2 oxygens because each oxygen is a 2-. And so all we do is simple algebra now. So what must X be? Well, X must be +4. It must be +4. And so that tells us that the carbon dioxide, carbon has an oxidation number of 4 positive. Oxygen has an oxidation number of 2 negative. And what I'm going to do is I'm actually going to draw the structure. You do not need to be able to do this. This what I'm doing right here is just to help us understand and kind of visually see it better. This is the Lewis structure for carbon dioxide. We know that each oxygen is a 2 negative, so each one is a 2 negative. We know that the entire thing has an overall charge of 0. So we know the entire thing has an overall charge of 0, and so what must this be to make it an overall charge of 0? It must be a 4 positive. Now, I want to kind of explain where these 4 positives and negatives are. And again, what I'm doing right now here, you will not be asked to do it in this way. I'm just kind of showing it to you in a different way to help you understand. And also what I'm about to say right now, you don't need to understand it to this level. All you will be asked to do is assign oxidation numbers, but I'm going to explain to you a little bit more why carbon is a 4 positive. And the reason why is because these bonds here, these bonds have electrons in there, and oxygen is more electronegative than the carbon. And so what happens is these electrons get pulled in that direction. These electrons get pulled in this direction, and that's 4 bonds that are being pulled away from carbon. That's 4 sets of electrons, which is where this 4 positive comes from, because those 4 sets of electrons are being pulled away. Now, this does not mean that the carbon has a charge of 4, because the carbon is participating in a covalent bond where the electrons are being shared. It's just that the oxygen is pulling those electrons away from carbon, and so there's an unequal sharing of electrons. So again, this 4 positive is not the charge, it's the oxidation number. It's different. Now, this 2 negative is coming from the fact that those 2 sets of electrons are being pulled towards the oxygen. So again, that's sort of where we get those oxidation numbers from. But again, you don't need to explain it in that depth. You only need to actually come up with these numbers here. And these numbers will be important in the future when we talk about electrochemistry. So let's go ahead and do number 5. Again, number 5, it's a polyatomic ion. So it's not a ionic compound per se because these are covalently bonded together. A polyatomic ion is a group of covalently bonded atoms that have an overall charge. And so what we're going to do is we're going to start with number 3. We assign oxygen a 2 negative. We don't know what sulfur is, so we call it X. But we know that whatever sulfur is plus, there's 4 oxygens right there, and each oxygen's a 2 negative. And we know that this must add up to the overall charge, and look at what the overall charge is. The overall charge is a 2 negative. And so now we just do some simple algebra. This is 8, so that means that this must be 6 positive. And when I say 8, this is 8 negative. So that means X must be 6 positive. So sulfur is 6 positive, oxygen is 2 negative. All right, let's go ahead and talk about this chemical reaction here. All right, so there's a chemical reaction, and what we're going to do is we're going to assign oxidation numbers and determine what is being oxidized and what is being reduced. And so notice how this here is an element. It's alone by itself. So whatever its overall charge is its oxidation number, which is 0. So this is 0. Now this right here, if you take a look, this has 3 elements, and again what we do is we are going to do this right here. All right, we're going to assign hydrogen a 1 positive, and then what you do is you assign oxygen a 2 negative, because according to rule number 3 that's what you do. And then what we do is we're going to solve for X. Now when we set this up, you do not need to consider this coefficient when you are solving for this. You do not need to do that. Instead, we can just assume it's or pretend it's not there when we are solving for X. We know that hydrogen's a 1 positive, plus we don't know what X is, plus there's 3 oxygens and each one's a 2 negative. and that must add up to the overall charge of the substance, which if you take a look is a 0. And so we just solve for x here, and if you solve for x, if you do some simple algebra, you'll see that x must be 5. So this is a 1 positive, nitrogen is a 5 positive, and this is oxygen's a 2 negative. So again, each element is getting its own oxidation number. And I mean, I can simplify this as 1 plus x plus 6 negative, and then so that's x plus 5 negative, so that means that x must be 5 positive. All right, next one. Oxygen's a 2 negative. This is a 4 positive because there's 2 of those oxygens there. This is an ionic compound, so the 10 is making a 4 positive charge in this situation because each oxygen is a 2 negative, so that means the 10 must be a 4 positive to balance that out. Again, oxygen's a 2 negative. We don't know what nitrogen is, but we know that this plus there's 2 oxygens right there. Each oxygen's a 2 negative, so that means that X is a 4 positive. Now, if you take a look here, this is a 2 negative, this is a 1 positive, according to the rule 3 there. All right, and so those are the oxidation numbers for each element. Now, what we're going to do is we're going to take this a step further because this is what we're starting with. These are the reactants. These are the products. And so what we're going to try to determine is we're going to try to determine what elements are being oxidized and what elements being reduced. And again, an oxidation reduction reaction is one in which electrons are transferred from one element to another. Now, we did learn the phrase, Leo the lion says grr. Leo the lion says grr. If something loses electrons, it's oxidized. If something gains electrons, it's reduced. And so what you want to do is you want to identify what elements have oxidation numbers that are changing as you go from reactants to products. And so this one right here is one. So here's one where there's a change. And then the other one is the nitrogen. And I'm gonna go about this with this one. It's the nitrogen. So the nitrogen has oxidation number that's changing. The tin also has an oxidation number that's changing. So let's go ahead and talk about the tin. The tin is 0, and it's going from 0 to 4 positive. So is it gaining electrons or losing electrons to become more positive? Well, again, electrons are negative. We have to remember that they're negative. So when electrons are lost, something becomes more positive. And so if you're losing negative charge, you become more positive. So tin must be losing electrons to go from 0 to 4 positive because it's becoming more positive. And if it loses electrons, it's oxidized. So this is being oxidized. Now the nitrogen is going from 5 positive to 4 positive. So how does it go from 5 positive to 4 positive? Well, it must be gaining electrons to do that. It's got to be gaining negative electrons to become less positive. And so if it's gaining electrons, that means it's being reduced. Whenever you have a chemical reaction in which oxidation occurs, that means there also must be reduction, and vice versa. If you have a chemical reaction where a reduction is occurring, there also must be oxidation occurring as well. You have to have both oxidation and reduction at the same time, because if something is losing electrons, then that means something else must be gaining those electrons. And so there are some chemical reactions, though, where you do not have either oxidation or reduction. And so if a chemical reaction is not being oxidized or reduced, or it doesn't have elements that are being oxidized or reduced, that means it's not a redox reaction. Go ahead and check out the answer key to these practice problems. Give these practice problems a try. It really comes down to practicing it that's really going to get this down. All right? If you have any questions, feel free to ask me in class, and you have a great day.